All right, welcome back everyone. So in this previous video, I covered chapter 1. So if you're following along on your course objectives, you should have been able to fill out basically the first 2 pages. So we went through uh, the process of natural selection, we talked about the scientific method and so forth. So in today's video, we're going to cover chapter 2, so the remainder of your course objectives. So let's go ahead and get that PowerPoint up. Where did it go? There it is. Okay, so we're going to get into chapter 2. So last time we were talking about the hierarchy of life. So we talked about the cells being the smallest unit of life, and then the things inside the cells are not considered alive, but they make up the cell's function, allows it to function, such as the organelles, which are made of molecules and so forth. So we're going to start small and work our way up throughout this term. So we're going to look at, this week we're going to look at the chemical complexity of biology, of life. So we're going to take a look at the smallest components that are inside a cell. We're going to look at the atoms and the molecules. So this unit, or this chapter, is divided into basically 5 different sections. So we're going to talk about what is matter. We're going to take a look at the elemental properties of matter. So we're going to get into things like the difference between an oxygen atom versus a carbon atom and so forth. And then we're going to introduce chemical bonding, so how 2 atoms join together to form a molecule or a compound. And then we'll get into chemical reactions where molecules, multiple molecules can interact together to have a reaction to form other compounds and other molecules. And then we'll also talk about hydrogen bonding and so forth. So how does life on Earth depend on the chemistry of water? So we're also going to touch on the properties of water and learn why every living thing contains water and needs it for survival. So we're going to talk about chemistry today. So let's start out by defining some different terms here. So first of all, what is matter? So matter is anything that takes up space and has mass. Okay, so that could include you're made of matter. The air is made of matter, even though you might not think it has mass. It does have mass to it. The molecules are just further apart. Water is made of matter. All of those living things, non-living things, anything that takes up space and has mass is considered a form of matter. And elements are basically things that we cannot break down to other substances. So they cannot be broken down chemically to other substances. So you might be familiar with elements of the periodic table if you've ever taken chemistry before. So, hydrogen is an element. Carbon is an element. Oxygen is an element. So these are substances that cannot be broken down into other substances. So basically, if we broke an oxygen atom down, it would not form a different substance. Okay? Compounds, those are substances consisting of 2 or more elements at a fixed ratio. So for example, table salt. Table salt is basically 1 atom of sodium and 1 atom of chlorine together, held together with a bond. And so it's at a fixed ratio, and you can see that it's forming table salt. And what's interesting about these two, look at sodium is in a mineral form, or solid form, and then chlorine is usually in a gas form. But when they come together, they form little crystals of salt. Water, H2O, is basically 1 oxygen atom bound to 2 hydrogen atoms. Okay. So if we take a look at basically you and broke you down into elements, most of you would be basically just 4 different elements. 96% of you would just be composed of 4 different elements: oxygen, carbon, hydrogen, and nitrogen. Okay, so you can kind of see it broken down here in this figure. So about 65% of oxygen, carbon's about, 19%, hydrogen's about 10%, and so forth. So we are basically just 4 elements. 96% of our body is made of 4 elements. And that's it. The rest, the other 4%, majority of that is made of calcium, potassium, and phosphorus is the P, and sulfur. Okay, so that's the other 4%. So that adds up to about 100%. But there is, so basically we're just 8 elements total. But there are these little trace elements that make up less than 1/100%. And that is just basically elements that we just need in very, very minute quantities. So we still need them. They're essential to life, but we just don't need very much of it. So, if you're any chemistry majors, or if you've taken chemistry classes, you might recognize some of these elements. But, if you're not, don't worry, you don't need to memorize them. But iron, iodine. So here's an example of somebody who doesn't have enough iodine in their diet, and your iodine is actually used in your thyroid. It helps produce hormones and things like that. So the lack of this iodine in this person's diet caused a goiter to form in the thyroid gland. So you can see how just not having a particular, minute element can lead to a health condition. So that's iodine. That's one of our trace elements. Boron, chromium, cobalt, copper, fluorine, and manganese. Those are the ones that round off the rest. So we just need them in minute quantities. Okay. So this is a table from your textbook that basically it just kind of shows everything for you if you want to highlight it. So again, about 96% of you is basically just 4 elements, and then about the rest of it is made up of smaller quantities, and you have the trace elements at the bottom. Okay. Okay, so let's get into, so we talked about matter, so let's talk about the element. So an element, again, is a substance that cannot be broken down into other substances. And an atom is the smallest unit of an element. So think of, for example, an atom of oxygen. Okay, so an atom of oxygen has basically 3 what we call subatomic particles. So it has protons, it has neutrons, and it has electrons. And you can see, here's an example. It's not oxygen. This one is helium. And in this case, helium has 2 protons. And you can see that the protons are located in the center of the atom, which we call the nucleus of the atom. Also in the nucleus of the atom is the neutrons. Okay, so the protons and the neutrons are found in the nucleus of the atom. Circling the nucleus of the atom is the electrons. So the electrons, because they have an electronegative charge, and then the protons have a positive charge, they can't be together, right? So they're kind of opposing charges there. So the electrons circle in the electron cloud surrounding the nucleus. So our helium atom has 2 protons, 2 neutrons, and in this case you can see the 2 electrons circulating the electron cloud. So when we look at the periodic table, we'll notice usually we have a symbol. So in this case, this one's the symbol for sodium. So we have Na is the symbol for sodium. And then you'll notice there's these 2 numbers that come along with it. So the bigger number is called the mass number. And the mass number is the number of protons plus the number of neutrons. Now you might be wondering, well, what about the electrons? Electrons have very minute amount of mass, so it's so negligible that it's not usually added into, it won't affect the mass number if we add them in. So our mass number is basically just the number of protons and the number of neutrons. And then the smaller number is the atomic number. So the atomic number is the number of protons found in that element. So all sodium atoms all have 11 protons. You'll never find a sodium atom that has 12 protons because it's not a sodium atom anymore. Okay, that would be a different element. So our atomic number is the number of protons. And for sodium, it's always going to be 11. The mass number might change because we might have different numbers of neutrons, but for sodium, it's always going to have 11 protons, so its atomic number is always going to be 11. In this case, you can see the mass number is 23. So if we know that there's always going to be 11 protons in this sodium atom here, how many neutrons would it have then? Okay, so basically we know that there's 11 protons. Total mass number is 23. So how many neutrons does that mean? So there's going to be 12 neutrons in this particular atom of sodium. So 12 plus 11 equals 23. Okay. Now, the neutrons and the protons each have a mass of approximately 1 Dalton, which is basically a unit of measurement that we use. So we can estimate the atomic mass, which is basically the mass of one atom, as being 23 Daltons. So think of the protons and the neutrons in this sodium atom each have a mass of 1 Dalton. So if there's 23 protons and neutrons total, then the atomic mass would be 23 Daltons. Okay. All right. So we talked about how the atomic number doesn't change. The number of protons, therefore, does not change. But the number of neutrons does change within an atom. So if we have two atoms that have the same number of protons but different number of neutrons, we can call them isotopes. So isotopes are two atomic forms of an element that differ in the number of neutrons. So here's an example down here. We have 3 different carbon atoms, carbon 12, carbon 13, and carbon 14. Now they all have the same number of protons. Okay, there's 6 protons in every carbon atom. It doesn't matter which one we're talking about, they all have 6. But the number of neutrons changes. Okay, so carbon 12 is indicating the mass number. Okay, so that means that there must be 6 neutrons to add up to 12. Carbon 13 must have 7 neutrons to add up to 13. And then carbon 14 must have 8 neutrons to add up to carbon 14, or 14 as the mass number. So isotopes have the same number of protons, hence they're the same element, but they have different numbers of neutrons. Now these isotopes, they can be really helpful in the study of biology, particularly radioactive isotopes. So radioactive isotopes are isotopes that decay spontaneously, giving off particles and energy. So basically what I'm talking about here is we might have something like carbon 14, which is an isotope of carbon and happens to be radioactive or unstable. And because it's unstable, it wants to give off energy. It might actually give off other things in the process. And by giving off energy, it can end up having dropping its mass. Okay, so it's still carbon because it has the 6 protons, but it may have ejected some neutrons to bring it down to carbon 12. So it's spontaneously giving off particles and energy. And this can be used in helping us understand how old certain fossils are, looking at certain elements through metabolic processes, diagnosing medical disorders, and so forth. So here's a checkpoint question. A nitrogen atom has 7 protons and its most common isotope has 7 neutrons. A radioactive isotope of nitrogen has 9 neutrons. So what is the atomic number and mass number of this radioactive nitrogen? So what do you think? First of all, what's the atomic number? Well, the atomic number equals the number of protons. And if there's 7 protons in every nitrogen atom, the atomic number is still 7, right? What's the mass number? Okay. Well, we're adding 7 plus the number of neutrons. In this case, there's 9, right? So the mass number would be 16 for this particular radioactive nitrogen. Okay? All right. So we've been talking so much about protons and neutrons. What about those electrons? Well, electrons, they are always in that cloud that surrounds the nucleus. And they actually have different energy levels of electrons. So we're going to talk a little bit more about those electrons. So electrons of an atom, they have something called potential energy. So potential energy is the energy that matter has because of its location and its structure. And in this case, energy, by the way, is just the capacity to cause change. So as those electrons are circling the nucleus, their distance from the nucleus can determine their potential energy. So changes in potential energy tends to occur in steps of fixed amounts. So an electron's energy level is correlated with its distance or average distance from the nucleus. So let me show you what I mean in this this diagram here. Okay, so electrons. Here's the nucleus of the atom. Remember, that's where the protons and the neutrons are. The electrons are going to be circling the nucleus of the atom. And electrons are found in electron shells, different electron shells. And each electron shell has a different distance from the nucleus of the atom. And basically, the closer distance you are to the nucleus, the lowest energy level it would be. The further distance you are from the nucleus, the higher energy level it is. Okay, so we can judge how many electrons, if we know there's a certain set of electrons per atom, per element, and we can see how much energy is in each level, electron shell level, based on its distance from the nucleus. Okay. So let's take a look at the periodic table. And this is going to allow us to judge the distances of those electrons. So here's just the first 3 rows of our periodic table. And you can see we have our first element, hydrogen. So hydrogen has 1 proton, so that's its atomic number, and it has 1 electron. So here's the nucleus of that hydrogen atom, and you can see that its electron is circulating the nucleus of the electron of the nucleus there. So what it's doing is it's hanging in the lowest energy shell, which is the first shell. There's not enough energy to bump it into the next shell. Helium has 2 electrons total, and it's going to fill out its lowest energy shell first. So it has its 2 electrons and it fills out this electron shell. So the first shell always has a maximum of 2 electrons in it. So we cannot have more than 2 electrons in this first electron shell. So you can see helium actually has exactly the amount it needs to fill its first shell. So helium happens to be a very stable atom because its electrons fill that shell. If we drop down to lithium, lithium has 3 protons, so that means it has 3 neutrons, or excuse me, 3 electrons. So it's going to take 2 of its electrons and fill the first shell. So there's the 2. So it's filled the first shell. And then it has 1 electron in its second shell. Okay. Now that second shell can have at most 8 electrons. So it basically has this one extra electron hanging around in that outside electron shell, the second shell. But the first shell is filled. Okay. If we look at carbon, carbon is the atomic number is 6, so there's 6 protons, 6 electrons. You can see how the first 2 electrons have filled the first shell, and then the rest of the electrons, all 4 of them, are evenly spaced along the second shell, but there's room for 4 more. Okay. If we look at oxygen, oxygen's another element that is very common. It's the most in our body. It has an electron number of 8 because there's 8 protons. And so you can see how it's filled to the first shell completely with its 2 electrons, and then it has 6 electrons in its second shell. So there's opening for 2 more electrons, basically, it needs to fill its outer shell. Neon has 10 total electrons, so it's filled its outer shell completely, so it's very stable. So you can see the ones on the far right, they've all filled their electron shells, their outermost shells, so they're going to be very, very stable. If we look at the third shell, it goes by the number 8, just like the second shell. So in order to fill that third shell, you need a total of 8. Okay, so these the chemical behavior of these elements, these atoms, are going to be determined by the spacing of their electrons and where they are in the periodic table. So something like sodium, for example, sodium has 11 electrons. That means that it's filled its first 2 shells, but then it has this third shell that just has 1 electron in it. So there's no way that it's going to fill the third shell. So it's going to be really reactive. It wants to get rid of that outer electron so it can drop down to a more stable electron shell. So we call that outer shell the valence shell. Okay, so chemical behavior of an atom depends mostly on the number of electrons in its outermost shell. So sodium has just 1 electron in its outermost shell, or valence shell. Okay, so valence electrons are those that occupy that valence shell. So sodium has 1 electron in its, or valence electron in its valence shell. Okay, those that have completed their valence shells, meaning they've filled out their outermost with the correct number of atoms or electrons, are considered unreactive. Okay, so that's where they want to be. Otherwise, if they haven't filled out their outermost shell, their valence shell, they're going to be very reactive. Okay. So let's take a look at our first checkpoint questions here. So how many electrons and electron shells does a sodium atom have? How many electrons are in its valence shell? So let's locate sodium. There it is. Okay. So how many electrons does it have? Well, its proton number is 11, so it also has 11. And how many shells does it have? Well, it has 11 total, and we know that the first shell can have a maximum of 2. The second shell can have a maximum of 8, so that's 10, so it must have 3 shells. Okay. How many electrons are in its valence shell? Well, it's filled out the first shell, it's filled out the second shell, and it has 1 in the third shell, the valence shell. Okay. So that's going to make it very reactive. So that's where we get into chemical bonding. So chemical bonding is when those atoms, they want to interact and complete their valence shells. So that sodium atom has this 1, electron in its outermost shell. So it's going to be reactive. It wants to fill its outermost shell. Now, obviously, it's not going to gain 7 electrons. That'd be way too much. But maybe it can get rid of that extra electron it doesn't need, and then it can drop down and just have 2 shells instead of 3, and that will make it more stable. So it's going to want to form chemical bonds with other atoms. So we're going to talk about those chemical bonds. We have 3 of them, in fact, that we're going to talk about: covalent bonds, ionic bonds, and hydrogen bonds. So let's talk about the first one, covalent bond. So covalent bonds, that's where the two elements are going to share their electrons, okay? So in this case, they are not going to be giving up an electron or gaining an electron. They're just going to share the electrons together in their outermost shell to complete their shell. So here's an example. We have two hydrogen atoms. Now remember, hydrogen just has one proton, so that means it only has one electron. And how many does it want? Well, to fill out the first shell, it needs two. So it wants two electrons, but it only has one. So if this hydrogen atom has one electron floating around, and this one has one electron, maybe they can kind of get really close together and share the electrons to fill out their outermost shells. And so that's called a covalent bond because they're sharing the electrons. They're sharing them. And this type of bond happens to be very, very strong because they don't want to give up the electron that they're sharing because then their valence shell will not be filled. So they're going to hold on tight to each other to share those electrons. Now in this case, this hydrogen molecule and this hydrogen molecule, they're each sharing an electron with each other. So we call that a single bond because they're sharing one pair of electrons. And so when we write it out, we can write it out like in stick form. So one horizontal line means a single bond. Oxygen has 8 electrons total. So if we have an oxygen atom that has 8 electrons, so let's say this is an oxygen atom, the first 2 electrons are going to fill out the first shell. And then the second, we have 6 left, so we might have those, and then it still needs 2 more to fill out its shell. So maybe it'll join with another oxygen atom with its 6. Okay. And then basically what it can do is it can get really close and share the other 2 electrons with each other. So by sharing the electrons, it's going to fill its outermost shell. Okay, so it has, let me pause that. So in order to share that electrons, okay, we need to maybe let's push these electrons to the side. Okay, so I'm going to get rid of those. Now we have them over here. And then these electrons, let's push over to the side as well. Let's get rid of these. And now they can share these 2 sets of electrons. So this is basically forming a double bond. So they're actually sharing not just one pair of electrons, they're sharing 2 pairs of electrons. And by sharing 2 pairs of electrons, they end up having filling out their valence shells. Okay. Now, in this case, this is known as a compound because it's in fixed ratio, but it's also known as a molecule. So molecules are 2 or more covalently bonded atoms. So this is a molecule of oxygen gas, or O2. This is a molecule of hydrogen gas, okay, or H2. So molecules are 2 or more covalently bonded atoms. Okay. So let's take a closer look at some examples. So we already talked about the hydrogen gas with the 2. Here's the oxygen, a little bit better drawing here, so you can see how the oxygen atoms have filled their first shell, and then they want to fill their second shell, but they only have 6 electrons each. So they're going to share 2 of their electrons with each other to fill out their valence shell. Here's water. Water, remember, oxygen has 8 total electrons, so it has 6. Oops. So it has 6 in its outermost shell, and it can form a bond with 2 hydrogen atoms. So hydrogen, remember, has 1 valence electron, and it wants 2 to fill out its shell. So it might share an electron with oxygen, and this one might share another electron with oxygen. So in this case, we have a molecule of water that has 2 hydrogens attached to the oxygen through a covalent bond. And then finally, here's the last example. So methane, you can see the formula for methane is CH4. So there's 1 carbon atom with its 6 electrons total and 4 hydrogen atoms, each with 1. So with the carbon atom, it has 4 electrons in its valence shell because it has 2 in the first shell, and then the second shell only has 4. So it's going to bond with 4 hydrogens and share those electrons with those hydrogens. Okay, so that's going to form covalent bond with 4 hydrogens. Okay. All right. Now, in this case, when we're talking about covalent bonds, we're talking about sharing of electrons. And we can get that electron sharing through what's called electronegativity. So that's the atom's attraction for electrons of a covalent bond. Sometimes there might be an equal attraction to those electrons, and so the atoms will share the bonds equally, or share the electrons equally, I should say. So those are what we call nonpolar covalent bonds. So an example of that would be, let me go back, oxygen, 2 oxygen atoms together, they're going to be sharing those electrons equally. The hydrogen gas, where we have 2 hydrogen atoms, they share them equally because they're the same electronegativity. With our carbon and our 4 hydrogens, it's also going to be the electronegativity of hydrogen and carbon are very similar, so they're sharing that electrons. So these, the A, B, and D are all examples of nonpolar covalent bonds because the electronegativity of each of these atoms is similar to each other. And so they're equally sharing those electrons. Water is considered a polar covalent bond because there's an unequal sharing of electrons. Water tends to be very electronegative. Okay, so it's going to be more electronegative than the hydrogen's electrons. And so it's going to want to hold on to those electrons a little bit more than the hydrogens are allowed to hold on to. So it's not sharing equally. The oxygen is holding on to those electrons more often than the hydrogens get to. And so we have some change in the electronegativity, where one side of our water atom is slightly negative, and the other side, where the hydrogens are, tend to be slightly positive. And so we have this change in the unequal sharing of those electrons, because more often than not, they're going to be over on the oxygen side instead of the hydrogen side. And so we call that polar. So polar covalent bonds are where we have this kind of electronegative gradient, where we have one side kind of is more electronegative and the other is more electropositive. So here's a closer view of that. So you can see how the oxygen is more electronegative than the hydrogen. And so those shared electrons get pulled more closer to the oxygen than the hydrogens. And so we end up with these partial negativities with the oxygen side and a partial positive charge on the hydrogen side. So this is considered a polar covalent bond. All right. So here's an example again. We have our hydrogen and our oxygen we've talked about already. So that's nonpolar, equal sharing. Same with the methane. They're both very similar electronegativities, so they're going to be equally sharing. But then our water molecules, slightly negative, oxygen, slightly positive, hydrogens. Okay. So let's watch a video kind of explaining that.
A covalent bond is the sharing of a pair of outer shell electrons by 2 atoms. For example, each of these hydrogen atoms has 1 electron in its outer shell, but needs 2 electrons to complete its outer shell. If the 2 hydrogen atoms share electrons, they can both complete their outer shell. The shared pair of electrons constitutes a covalent bond, shown in shorthand as a line. The covalently bonded hydrogen atoms form a molecule of hydrogen gas. A molecule is defined as two or more atoms held together by covalent bonds. An oxygen atom needs two electrons to complete its outer shell. Two oxygen atoms can share two pairs of electrons. A molecule of oxygen gas is held together by a double covalent bond, two shared pairs of electrons. A carbon atom needs four electrons to complete its outer shell. It can share electrons with four hydrogen atoms, forming a methane molecule containing four single covalent bonds. Methane is a compound, a substance formed by the combination of two or more elements. We call methane natural gas. It is the fuel burned in gas stoves and furnaces. An oxygen atom needs two additional electrons to fill its outer shell. Thus it can form two single covalent bonds. An oxygen atom can share electrons with two hydrogen atoms, forming a molecule of water containing two single covalent bonds.
Okay, so that was a good visual, so you can see how they're sharing the electrons, and you saw how the methane and the oxygen gas and the hydrogen gas, those were nonpolar covalent bonds, whereas this water molecule is forming a polar covalent bond. So here's a question. What is chemically nonsensical about this structure? What do we see here? Well, how many electrons does carbon have? Remember? It has 6, right? So if it has 6, how many would it have in its valence shell? Well, it fills the first shell with the first 2, so that must mean that there are 4 in its valence shell. How many covalent bonds does this atom share here? There's 1, 2, 3. There's only 3 covalent bonds, so this doesn't make sense because it needs 4 covalent bonds and it only has 3, 1 with hydrogen and 2 with the carbons. So this doesn't make sense. We actually need maybe another hydrogen to form the 4th. Okay, maybe this one needs another hydrogen too. Now they can fill out their valence shell. Okay. All right, so we talked about covalent bonds where they're sharing the electrons to fill their outermost valence shell. So the next type of bond we're going to talk about are called ionic bonds. So in ionic bonds, instead of sharing the electron, they're going to either give away or accept an electron. And so they're going to form an ionic bond, which is an attraction between two oppositely charged ions. So an ion is a form of an atom or molecule that gains or loses an electron and becomes charged. So let's go back to the sodium example. Remember how sodium has 1 electron in its outermost valence shell? And it's not going to gain 7 electrons to fill that 3rd shell, its valence shell. It would be much easier just to get rid of that extra electron. Okay, so get rid of that extra weight. It doesn't need it. Then it would be more stable if it dropped down to having the valence shell at the 2nd level. So it wants to get rid of this electron. If it gets rid of it, if it loses that electron, then how many total electrons does that sodium have? Well, it would only have 6, right? Or excuse me, bleh. It would have 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And how many protons does it have? It has 11, right? So if it has 11 protons and only 10 electrons, it's slightly positive. So it's going to want to lose an electron and become charged. So it's going to have a positive charge because there's a slightly positive nucleus there. Chlorine, on the other hand, chlorine has 17 protons, I believe, so 17 electrons. And so if we look this up, 2 electrons fill the first shell, 8 fill the second, so that's 10. And then it just has 7 in its third shell, but it really wants 8. Okay, it really wants that last electron to fill its shell. So it's going to want to gain that electron. But if there's 17 protons and it gains an extra electron, now it has 18 electrons. So it's going to be a negative ion. It's going to have a charge of negative because it has more electrons than protons. Okay? So in this case, the sodium has lost an electron, became a positive ion, and the chlorine has gained an electron, became a negatively charged ion. So they form that weak bond. So that's called an ionic bond. They're not sharing electrons, they're gaining or receiving electrons from each other. So ionic bonds, when we talk about ionic bonds, we're always talking about between a positively charged ion that wants to get rid of its electron to become positively charged, and a negatively charged ion that wants to gain that electron. So the positively charged ion is called a cation. So it's going to be positively charged, such as sodium. Anions are the negatively charged ions. So chlorine would be an example of an anion. And then together they form an ionic bond because they're attracted to each other for that gaining and losing the electrons. Now, when we're talking about ionic bonds, these ionic bonds form what we call salts or ionic compounds. So table salt is between a sodium cation and a chlorine anion. And so that's why we call it a salt, but it's really just sodium chloride. Okay, so it's considered table salt. So let's watch a video showing that.
Sometimes atoms complete their outer shells by stealing or giving away electrons. This happens between sodium and chlorine atoms. An electron moves from the sodium atom to the chlorine atom. The outer shells of both atoms are now complete, containing 8 electrons. The chlorine atom now has 18 electrons but only 17 protons. Because an electron has a negative charge, the chlorine atom now has a net negative charge. Such a charged atom or molecule is called an ion, in this case a negative ion. The sodium atom has lost an electron, leaving it with an extra proton, which has a positive charge. The sodium atom has become a positive ion. Ions with opposite charges are attracted to each other, forming an ionic bond. These ions combine to form a compound with new properties. In this case, sodium chloride, ordinary table salt, is formed.
Okay, so you can see the difference between an ionic bond and a covalent bond. They're not sharing electrons anymore. So the ionic bond is a weak bond because, the sodium already got rid of its leftover it didn't need, and the chlorine got what it wanted, so they're not going to be hanging around each other anymore. So they have this weak bond that's forming through ionic bonds. So the last type of chemical bonding we're going to talk about is called hydrogen bonds. So hydrogen bonds are also a weak bond, just like the ionic bond, but it's between a hydrogen atom, could have guessed that, right? And a electronegative end of a nearby molecule. So here's an example of a hydrogen bond. So here we have a water molecule that's polar covalent, right? So that polar covalent bond causes a partial negative charge on one side and a partial positive charge on the hydrogen side. That hydrogen, is slightly positive, and it would kind of like to have some negativity near it, okay? So it's going to form a hydrogen bond with a nearby atom's partially negative side. So you can see this is an ammonia atom that is also a polar covalent. So that nitrogen is slightly negative. The hydrogens are slightly positive. And so this hydrogen atom of the water molecule is going to be attracted to the partially negative nitrogen part of this ammonia molecule. So they're going to form a weak bond. Okay, so it's not going to be as strong as a covalent bond. The water molecule will still hang together, but this hydrogen end of the water molecule is going to want to bond with this nitrogen end of this other nearby molecule. Okay, so let's watch a video showing that.
The atoms that make up a water molecule are in a constant tug-of-war over their shared electrons. Oxygen exerts a far stronger pull on the shared electrons than does hydrogen, and so the electrons spend more of their time closer to the oxygen atom. Because of this unequal sharing of electrons, the oxygen atom in a water molecule actually has a slight negative charge, and each hydrogen atom has a slight positive charge, even though the water molecule as a whole is neutral. Because of the unequal sharing of electrons and the resulting positive and negative poles, a water molecule is said to be polar. The polarity of water molecules causes them to be attracted to each other. Since the positively charged atom involved in this special type of attraction is always a hydrogen atom, this kind of bond between molecules is called a hydrogen bond. Each water molecule can hydrogen bond to 4 other water molecules. A hydrogen bond is weak and lasts only a tiny fraction of a second, but it takes a lot of energy to overcome the combined attraction of many hydrogen bonds. This explains water's great capacity to store heat, its high boiling point, surface tension, and several other unusual properties.
Okay, so one important thing that you got hopefully from the video is that the water molecule itself is held together by a polar covalent bond. But they have an attraction, water molecules in general have an attraction to each other, to nearby water molecules, via a hydrogen bond. So sometimes students get that a little confused. Okay, the molecule itself is held together with a polar covalent bond, but they have an attraction to nearby water molecules to form a hydrogen bond. So what enables neighboring water molecules to hydrogen bond to one another? Well, it has to do with that water structure. Remember, the oxygen end has a negative or partial negative charge. The hydrogen end has a partial positive charge. So because of that, the hydrogen end is going to be attracted to another nearby molecule's negative end. Okay. All right. So moving on, aside from covalent bonds and ionic bonds and hydrogen bonds, we also have other kind of chemical bonding that takes place. So here's an example of one that we're going to mention called van der Waals interactions. So van der Waals interactions are where we have electrons that are distributed asymmetrically in molecules and atoms. So we end up with kind of a partial charge on one, partial positive charge on one end, negative charge on the other. And so that enables atoms and molecules to end up sticking together, and they form these little weak bonds with one another. So this explains why something like a gecko can climb glass. So it has to do with slight little van der Waal interactions that the gecko has on its toe pads with the surface of the glass. Now these weak bonds, they're very weak. They only last a microsecond, but it just allows the molecules from the glass to stick to the molecules of the toe pads of that gecko just long enough that it can start moving up the glass. So van der Waal interactions are just kind of another type where we have molecules sticking together for a brief period of time with weak bonds. All right, so here's a question for you. Based on the periodic table below and what you know about ions forming, which elements will most likely form an ionic bond? So let's do that one first, and then we'll get to the covalent bond. Well, we know sodium and chloride too, right? So we have the sodium is located here. So it's got 1 valence electron. And then the chlorine is located over here, and it has 7. So they're going to want to form an ionic bond. Let's see, chlorine and oxygen, or carbon and oxygen. Carbon has 4, oxygen has 6 valence electrons, so that's not going to form an ionic bond because nobody's going to want to give up an electron. Nitrogen and oxygen, well, that one has 5, this one has 6. There's no way they're going to give up an electron. How about silicon and chlorine? So silicon is right here, chlorine's right there. Nope, same thing. So there's 4 in silicon. Looks like 7 in chlorine, so they're not going to want to give up their ions. How about hydrogen? Nope. So looks like this one's the only one that will form a covalent bond, or excuse me, a hydrogen bond. Okay. Now, which one of these do you think will form a covalent bond where they can share? Well, in that case, we already talked about how 2 hydrogen atoms, they can share an electron to fill out their outermost shells. So this one would be an example of a covalent bond. That one would be an example of an ionic bond. Okay. All right. So if we take a look at these models, molecule size and shape are key to its function inside the cell. So molecular shape determines how biological molecules recognize and respond to one another by their shapes. So you can see that water, we already know, is this polar covalent bond. And so it has this type of shape to it. And so that's going to lead to that kind of partial negative end and a partial positive end, right? Whereas methane, its shape determines its function. In this case, it's forming covalent bonds with hydrogen. And so it's going to have more of a stable shape. It's not going to react as much as water. So this is more non-polar covalent. So the reason why I bring up shape and structure is because biological molecules, they can mimic one another. So biological molecules may bind temporarily to each other through weak interactions if their shape complements each other. So the molecules with similar shapes, they probably have, similar biological effects. So they can be what we call a molecular mimic. So here's an example of a molecular mimic. We have a natural neurotransmitter called endorphin, and then we have morphine. And you can see that here's a brain cell. This big thing is a brain cell, and you can see this. We have this endorphin receptor site on the surface of the brain cell. And this receptor site has a certain shape to allow a molecule to bind to it. And that molecule that it binds is the natural endorphin. So this endorphin receptor is perfectly matched to the endorphin molecule. But morphine has a very similar structure. So look at the natural endorphin structure, look at the morphine structure. That's pretty similar, and it can actually end up being received by the endorphin receptor site. So these two molecules, endorphins and morphine, are biological mimics, okay? They are very similar in shape to each other, so they can bind to the same receptor site. Okay, all right, so let's move on. So we talked about chemical bonding, we've talked about elemental properties and atoms and matter and things like that. So now what happens when we take two molecules and we have them react? So chemical reactions change reactants into products while conserving matter. So when we're looking at a chemical equation, we're seeing how two molecules, or in this case, three molecules, reacting together. So those are called reactants. And then the product is what ends up happening to them, okay? So in this case, we have two hydrogen gas atoms. Okay, so here's one, here's another one, and then we have an oxygen gas atom. And these three molecules, or compounds, they're going to be interacting with each other, and they end up forming two water molecules in the process. So we now have 2 water molecules being produced from this reaction. Now, all reactions are theoretically reversible, so if I can take 2 hydrogen gas compounds and combine them with oxygen gas, I can form two water molecules. And theoretically, I can take 2 water molecules and break them down into an oxygen gas compound and 2 hydrogen gas compounds. So this technically is reversible, theoretically. But there's some laws of energy we'll talk about later on, and not in the next couple weeks, that prevent this from being completely reversible unless we add energy to the reaction. Okay. So chemical equilibrium is reached when the forward and reverse reactions are equal. So if these are going at the same time, so these reactants are reacting together to form water, and the water is breaking apart to form these over and over again, they've reached a chemical equilibrium where it's equal on both sides. Okay. All right, so let's take a look at an example of a chemical reaction in nature. So photosynthesis is a very important chemical reaction. Our lives depend on photosynthesis because we end up getting the product of photosynthesis, glucose, and eating it for nutrients that powers our cells. We also get the other product, oxygen, that we use in cellular respiration, a metabolic process. So here is what goes into the reaction. Our reactants are carbon dioxide and water. So plants, they absorb carbon dioxide through their leaves, and they absorb water through their roots. And in order for these molecules to react, they need energy. Now, where they get that energy is from the sun. Light energy is powering this reaction. So light energy from the sun allows the reactants to react to form the products, in this case, glucose and oxygen. Okay. So those products came from these molecules. We can even add them up. If you notice, we have carbon dioxide, so CO2, we have 6 of them. And each carbon dioxide is made of 1 carbon and 2 oxygen atoms. So the carbon is in black, and then the oxygen are these little red ones. So if I have 6 total carbon dioxides, that means I have 1, 2, 3, 4, 5, 6 total carbons, right? Well, in my reaction, that means that my glucose molecule should have 6 carbons because there's nothing in oxygen. Okay, so there is 6 carbons in the glucose molecule. So that means that it's a balanced equation. Okay. All right, so we talked about chemical reactions. Next, we're going to get into the properties of water. So at the beginning of this lecture, I talked about how water is the most important thing for life. So most important molecule for life. So all living things need water, and they're mostly made of water. So a hydrogen bond, so we're going to look at the properties of water. And one unique factor with water is that hydrogen bond forms. So remember, again, I'm going to kind of drill it into you. The molecule itself is held together by what type of bond? The oxygen and the hydrogens are held together by a polar covalent bond. Water of nearby molecules are held together with a weak bond called a hydrogen bond. So hydrogen bonds form when the slightly negative charged oxygen and one water molecule and the hydrogen slightly positive end of a nearby water molecule interact to form this bond. So this is something that's going to contribute to the various properties of water that really help living things survive. So we call those emergent properties. So they contribute to Earth's suitability for life. And we're going to go through 4 of them. So we're going to talk about how water is cohesive, how water is able to moderate temperature, how water expands when it freezes, which is actually really unusual for a molecule. And we'll talk about the versatility as a solvent. All right. And of course, what better person to explain it than the Amoeba Sisters video? So we're going to watch that.
So we have a riddle for you. Okay, not really a riddle. We're bad at riddles, but more like clues about our favorite molecule. It's polar, it's shaped like an outstretched V, its properties are awesome, and it makes up 3/4 of the surface of the Earth. That one always gives it away. Our favorite molecule is water, and we're not going to lecture you about how important water is and the fact that all life as we know it could not survive without it, because, yeah, that's true. But we really want to talk about what makes water so unique for biology itself. What are some awesome properties of water? Now, we mentioned the shape of water and the fact that water is polar. It has one very electronegative oxygen that is always trying to keep the electrons closer to it than to the hydrogens it's bonded to. And this actually gives oxygen a slightly negative charge because of the electrons that are spending more time next to it, and it gives the hydrogens a slightly positive charge. Well, that means that other water molecules have an easy time bonding together. Why? Well, because the hydrogen of one water molecule with its slightly positive charge can bond to another water molecule's oxygen with that slightly negative charge. These bonds among the water molecules are hydrogen bonds, and these are the very bonds that allow water to have many of the properties that we're about to talk about. Have you ever looked at a really tall tree and wondered, how does the water get all the way up there? I mean, it's got to go against gravity. Gravity? Well, in our plant video, we talk about the xylem. It's vessels within certain types of plants, like trees, and these vessels transport water. But what's really neat about water is that it sticks to the xylem walls in what is known as adhesion, and this helps fight gravity. But water molecules, with their hydrogen bonding, they also bond to each other in something called cohesion. It's almost a beads on a string kind of fashion. Water molecules evaporate from a leaf, and then the next water molecule in line is pulled upwards, and so on. This cohesion is really a big deal. Cohesion is also a reason that water striders, one of our favorite insect types, can skate on water. Cohesion contributes to the surface tension of water. Water actually has quite a bit of surface tension compared to many other liquids. And it's not just water striders that can walk on water. There are a lot of insects, spiders, and even larger animals like reptiles and some birds that have the ability to walk on water. So, to the Google for that. Now, with water being polar, it's also a very powerful solvent for other molecules. And that means that water can dissolve many other molecules, especially polar molecules and ionic compounds. Now, why does that matter? Well, this is really important because many of the processes that occur in organisms use water as a solvent. In our body system video, we talk about the function of kidneys, and you definitely couldn't have kidneys doing their function without water. Also, a main component for body fluids is water. I'll never forget when I was little, my father built us a pond. We had some goldfish in there, and I loved this pond. Well, in West Texas, where we're from, it can freeze in the winter. And one morning, I went outside, terrified to find that the top of the pond had frozen. And I thought our fish were goners. Only to find out that they were swimming and doing their fish activities under the ice layer. It's common for many substances to actually contract when they freeze and to become more dense. But water expands when it freezes and becomes less dense in its frozen state, resulting in floating ice, where it can actually make this insulated surface layer that makes a difference for many organisms underneath. And this is due to the hydrogen bonds. See, at freezing level, the making and breaking of hydrogen bonds, which usually happens pretty often, it's not happening very much when frozen. And so the molecules, they're set into this lattice of hydrogen bonded molecules, just far enough apart that it's less dense in ice form. than it is in water form, and that's going to be very important for all of that aquatic life. Speaking of temperature, water resists changing its temperature. It has what's called a high specific heat. Specific heat, it's a measurement of heat that's needed to be absorbed or lost for 1 gram of a substance to change its temperature by 1 degree Celsius. And that's why on the first day that school is out in the summer, it may be super hot outside, but the water could still be pretty cool. It's really good that water's like this for life. It's stabilizing for aquatic environment temperatures. And it also means that water can absorb a lot of heat in the summer without reaching as high of a temperature itself, which is useful when winter comes along, because then the water can release heat as it cools in the winter. This also impacts the environment. Now, still on the topic of temperature, consider evaporation. Many animals rely on evaporation to cool them. Think of water molecules. They are moving, but those that have more heat energy, they're moving the fastest. And they're the more likely molecules to make the phase change to gas. And these molecules, as they leave, their energy, their heat, is no longer on your skin. And by the way, all of this is not just animals, too. Plants use evaporative cooling to aid them in hot temperatures. Excessive high temperatures could be very dangerous for many different processes in both plants and animals. It can be damaging to the enzymes involved in those processes. So, that evaporative cooling is very important. Well, we went through a lot of features of water. Definitely something to consider next time you encounter it, which, based on how much we depend on water, will likely be soon. Well, that's it for the Amoeba Sisters, and we remind you to stay curious.
All right. So from that video, we looked at the different properties of water. So we're going to go over these properties in detail. So let's start out with the first property of water, which was its cohesiveness. And we got to define what cohesion is and adhesion to make sure we understand the definition so we can understand the concept. So cohesion, think co means two water molecules. They're clinging together. And the reason why they cling together is because of the hydrogen bonds that they form. So water has that ability to cling to each other through cohesion due to the hydrogen bonding. Adhesion is when we have water molecules clinging to another surface, so not a water surface. And so they're adhering to another polar molecule essentially. So this explains how water can move up a tree defying gravity. So the water is adhering, clinging to the side of the plant cell walls and being cohesive, interacting with each other to cling to each other. And so that's going to allow them to kind of move up the tree against gravity. Okay, so adhesion, the ability of water to cling to other surfaces, and then cohesion when they're clinging to each other. Okay. So after a hard workout, you may see beads of sweat on your face. Can you explain what holds the sweat in the droplet form? Well, that droplet form is a drop of a bunch of water molecules, right? And they are cohesive, so they're going to be basically clinging to each other to form that bead. All right. Another property of water is that water has a very high specific heat. That means that it needs to absorb a lot of heat to be able to break those hydrogen bonds, and it releases heat when those hydrogen bonds are forming. So because of that ability to absorb heat to break the bonds and to release heat to form the bonds, it's going to have a high specific heat. So water tends to absorb heat from warmer air and release stored heat in cooler air. And so water can absorb and release a huge amount of heat with only a slight change in its own temperature. Okay, so this is going to keep the temperatures relatively stable within the limits of that permitted life. So here's an example. You can see in Southern California, there's this big body of water, the Pacific Ocean, that's always about 68 degrees. And the cities that are close to the ocean, they're going to have a more stable temperature than the further inland cities because of that water, high specific heat, being able to hold in the heat and release the heat at a relatively stable rate. Okay? So that's different than the surface of the land that's not going to hold on to the heat as well or absorb, it can absorb the heat and so forth. And then this also leads to this evaporative cooling. So that's based on the water's high heat of vaporization. So it takes quite a lot of energy for that water molecule to move from one state of matter to another state of matter. So meaning it takes a lot of energy for that water to go from liquid form to gas form. You might have experienced that if you've ever tried to boil water on your stove. It seems like it takes forever. So that water stays liquid for quite a long time and then suddenly you start to boil. So evaporative cooling is based on water's high heat of vaporization. So that means once that water has moved to its vapor form, it's taking a lot of energy or heat with it. And so it's going to cool the surface it's left behind. So that explains why on a cold day, basically after all strenuous exercise, you're releasing a bunch of heat. And if you walk outside in a cold temperature, you see that steam coming off of you. So all that energy, all that built up heat inside your body is being released as the water is evaporated from the surface of your body. So it leaves you feeling cooler. So that's why we sweat. So explain the popular saying that says, it's not the heat, it's the humidity. So high humidity is going to be more uncomfortable than if it's low humidity and high heat. So for example, imagine if it's 100 degrees outside. If it's 100 degrees and the humidity is relatively low, you can sweat a lot and it'll cool yourself down because the water will evaporate. But if the humidity is high and it's 100 degrees outside, it's going to be harder for your the water to evaporate. And so it's going to be less likely that you're going to have the sweat evaporate to cool yourself down. So high humidity hampers cooling by slowing the evaporation of the sweat. So it makes it more uncomfortable. All right, so we talked about the high specific heat, the evaporative cooling, and so forth. So let's get into one interesting thing about water is that when it cools and it changes to a solid form, it actually expands. Okay, so this is pretty unusual. So in its liquid form, it's actually going to be smaller than in its solid form. So water molecules, they become less dense as solid water than they do as liquid water. So ice is going to be less dense than liquid water. And the reason for that is when it cools down, the hydrogen or the molecules will stop moving and they've formed their hydrogen bonds. And those hydrogen bonds are spread out in kind of a crystal form. And so that is going to be bigger or more expanded than in liquid form where they're going to be closer together. And that means that ice is going to be less dense and so it floats. So that's why when you have ice water, the liquid is going to be lower and the solid ice is going to be floating on the top. And this allows the fish from the Amoeba Sisters video to survive in the liquid water below in the pond, even if the surface is ice. Okay. So water, it actually reaches its greatest density at 4 degrees Celsius, right before it freezes. So explain how the freezing of water can crack boulders. So think about water in liquid form. So water in liquid form is smaller, so less dense, so it can squeeze in between a boulder. And then if the temperature goes down, it's going to freeze. And as it freezes, it expands. And so that way it can crack the boulder. Okay. So floating ice is very important for a lot of organisms because it insulates the water below. So it allows water, living things to exist, even if the surface is frozen. And so when we think of global warming is going to impact areas that are usually frozen for longer periods of time. It's going to impact them a lot differently. So things like the Arctic region is very vulnerable to changes in temperature because it's always right around freezing. So if the temperature is more towards the above freezing, then the water is going to become more dense and it's going to melt. If it's below freezing, then of course it's going to be less dense. And it affects all the living things that depend on having ice there. So having the ice insulate makes the organisms living under the surface of the ice warmer and they can move around more. Those on the surface of the ice, well, they have something to walk on, like the polar bears. Okay, so they're going to need the ice there so that they can do their hunting in the middle of the ocean, even though they're standing on the surface. So species, they tend to they can be harmed by the loss of the ice. And some species, they might benefit from the loss of the ice by allowing them to migrate further. So many of those bodies of water that are used to having that surface ice during parts of the year, they're going to be, disappearing because, or at least that environment that the organisms adapted to that particular environment might disappear due to global warming. And then finally, we're going to look at the property of water as water a universal solvent. So we need to get into a little bit of terminology there. So a solvent is the dissolving agent of a solution. A solution is a liquid that is a homogeneous mixture of substances. So basically a solution includes a solvent, the dissolving agent, and a solute, the substance that's dissolved. So when you have a solvent and a solute together, you form a solution. So an aqueous solution is one where we have water as the solvent. So think about, all the aqueous solutions you have made over the years. So you've made maybe put some sugar in water and mixed it around so that you can feed the hummingbirds or something like that. So sugar would be the solute, water would be the solvent, and then you're making sugar water out of it. And when you're doing that, you're taking the sugar molecules and they're going to be dissolved in that water. So the water is going to surround the different atoms inside that sugar molecule and separate them. Okay, so you can see how we have salt, sodium chloride has those weak ionic bonds, right? And when we have put salt in water, you mix it around, okay, the water molecules are going to start attracting the sodium and the chlorine. And so it's kind of breaking down the crystals and dissolving them. So water tends to be a universal solvent. So why are blood and most other biological fluids classified as aqueous solutions? Well, because water is a solvent, right? And so that's why it's going to be dissolving all sorts of those substances. So this is important when we're looking at different substances because some substances have an attraction or affinity to water and some don't. So if a substance has an attraction or affinity to water, it's called hydrophilic. So think hydro as water, philic as liking. So water liking, it loves the water. Hydrophobic substances, they fear the water. They do not have an affinity to water. So think about, if you took vegetable oil and you poured it into a cup and then you added water to it. Would they interact together and dissolve together? Nope. Okay, so there's going to be a separation, right, between the oil and the water. So oil molecules are hydrophobic. And the reason why they're hydrophobic is because they have relatively nonpolar covalent bonds. So going back, what type of bonds, covalent bonds, does water have? Polar. So polar bonds tend to, want to hang out together. So hydrophilic substances tend to have polar covalent bonds or ionic bonds, and hydrophobic substances, they tend to have nonpolar covalent bonds. Okay, so that might help us when we're getting into next week with our macromolecules. So give you a heads up there. All right, so when we're taking a look at our aqueous solution, remember an aqueous solution is when the solvent is water, we can take a look at the solute concentration. And most chemical reactions in organisms, they involve solutes dissolved in aqueous solutions or water. And chemical reactions depend on the concentration of the solutes or the number of molecules in the volume of the aqueous solution. So if we have, something that has a high solute concentration, that means there's more molecules of that solute compared to the volume of the solution or the amount of the dissolving agent, water. So that's going to play a key role in looking at solute concentrations in aqueous solutions. Okay, so when we're talking about an aqueous solution, we're going to basically look at what the solute concentration is of that aqueous solution. So we need to figure out, first of all, what's the solute? And in that solute, we have to look at its atoms. So we're going to look at the atoms that are in that solute. So for example, we might look at sodium, salt. Okay, so salt is sodium and chlorine. So we're going to look at the mass of all of the atoms of that table salt in a molecule of salt. And that's going to form its molecular mass. So the sum of all masses of all atoms in a molecule. So let's go back to our table salt example. So table salt has I can't remember off the top of my head. Maybe we can use it as an example, but it's sodium and chlorine put together. So if we have all of the atoms of sodium, so one atom of sodium plus one atom of chlorine, we're going to get the molecular mass, the sum of all the masses of the atoms. The number of molecules are usually measured in moles. A mole is going to consist of 6.02 times 10 to the 23rd molecules. So 1 mole of sodium has 6.02 times 10 to the 23rd power molecules of it, okay? Whereas 1 mole of chlorine has 6.02 times 10 to the 23rd molecules of chlorine in it. Now, Avogadro's number states that the unit Dalton is defined as basically 6.02 times 10 to the 23rd Daltons equals 1 gram. So if we have 1 gram of table salt, okay, or I should say 2 grams of table salt, then 1 gram of sodium plus 1 gram of chlorine equals 2 grams of table salt. Okay, so each gram of sodium would contain 6.02 times 10 to the 23rd Daltons or molecules. So the molarity is the number of moles of solute per liter of solution. So the greater molarity indicates the greater solute concentration, the more amount of solute in that particular solution. Okay. So this gets us to the point of something called an acid versus a base. So acids and bases are how our water is going to be binding to the dissolving agent, that solute, and reacting with it. So our water molecule remember, wants to bind with hydrogen bonds, and it can undergo a reaction in the process. So if we have two water molecules, for example, they're going to react together and they can form what's called a hydronium ion, which is where we have one oxygen and three hydrogens. But that's a positive charge, right? Because the oxygen only needs 2 electrons, but the hydrogens have 3 total, so that's going to give it an extra positive charge. And then we might have our hydroxyl ion is the leftover, so that's the oxygen and hydrogen. Well, the oxygen has an extra electron, and so that's going to make it more electric charge. So it's got to have this negative charge. So that's why it's OH negative. So hydrogen ions, that's where that hydrogen is transferred from a water molecule to another, leaving behind a hydroxyl ion. Okay, so this hydrogen bond might end up causing that hydrogen to break off and bind to that oxygen, leaving behind an OH negative hydronium ion and forming a hydronium ion. So when water dissociation is rare and reversible, it's important in the chemistry of life. So hydrogen ions and OH negative hydroxyl ions are very, very reactive. So solutes are called acids and bases. They can disrupt that balance between the hydrogen and the hydrogen ion and the hydroxyl ions in pure water. So if we have a solute that's an acid, it's going to increase the hydrogen ion concentration in water. If we have solute that reduces the concentration of hydrogen ions, it's considered a base. So let's take a closer look at that. So acids, they increase hydrogen ion concentration in water. Bases, they reduce the concentration of hydrogen in the water. So we have 3 solutions here. We have a basic solution, we have a neutral solution, and we have an acidic solution. So in the basic solution, notice the hydrogen ion concentration. It's going to be less. So here, I'll do it right above. It has less hydrogen ions relative to the hydroxyl ion concentration. So that's going to form a basic solution. An acidic solution is the opposite, when we have greater hydrogen ion concentration to hydroxyl. Okay? And then a neutral solution is when they're about equal. All right? So here's an example. HCl is considered a strong acid. And the reason for that is when HCl enters water, it's going to break apart and form hydronium ions and then that chlorine. So it's going to form a strong acid because of the amount of hydrogen. The concentration will increase as it's dissolved. In this sodium hydroxide, this is considered a strong base because when it enters water, the sodium is going to dissociate and then it's going to leave behind this hydroxyl ion. So the concentration of hydroxyl ions will increase in that solution, making it a basic solution. Okay? So this leads us to something called the pH scale. So the pH scale is when we have the amount of hydrogen concentration within the solution. And it's defined as a negative logarithm of hydrogen concentration. So it's written as this, where you have pH equals a negative log of hydrogen ion concentration. When we have a neutral solution, that means that the ion concentration is we're going to have basically an equal amount of hydrogen ions to hydroxyl ions. And so our pH is going to end up being a 7 or neutral. Okay, so that means that the molarity of the solution is at a 10 to the negative 7 for the hydrogen ion concentration. So let's look at the pH scale. So the pH scale goes from 0 to 14. We already talked about 7. pH 7 is neutral, so that's when the hydrogen ions are equal to the hydroxyl and you get a pH of 7. Okay. If we move closer to 0, we're going to be increasing the amount of hydrogen ions. And by doing so, we're going to lower the pH. Okay, so that's going to lead to a higher ion concentration. So this is going to be more of a positive number. And so we're going to end up with, basically, it's going to end up with a smaller pH value. Okay. And so the higher the concentration of hydrogen, the more concentrated hydrogen ions get, the stronger the acid, the lower the pH. Okay. Basic solutions, it's the opposite. So the lower concentration of hydrogen, more hydroxyl groups. And so that's going to increase the pH. So higher pH equals basic solutions, lower pH equals acidic solutions. And as far as our biological fluids, they tend to exist right around neutral between 6 and 8. Okay. All right, so here's a question for you. Compared to a basic solution of pH 9, the same volume of an acidic solution at pH 4 has how many times more hydrogen? Well, this goes back to the pH scale being a logarithmic scale. Okay, so that means as we move up or down the scale, we're increasing the concentration. If we're moving up the scale towards the 0, we're increasing the hydrogen concentration by a factor of 10. So going from pH 6 to pH 5, there's not just 1 times more hydrogen ion concentration, there's 10 times more. So let's go from pH 9 to pH 4. So we have pH 9 and here's pH 4. So we're going to look at how much more hydrogen ion concentration pH 4 has compared to 9. So 9 to 8, 8 would have 10 times more than 9. So that's 10. Here's another 10. Here's another 10. Here's another 10. Here's another 10. So each one of these steps indicate a factor of 10. We got 5 of them, right? So basically, it's 10 times 10 times 10 times 10 times 10 concentration of hydrogen. So what's 10 times 10 times 10 times 10, or 10 to the 5th power? Because we did it 5 times. That's going to be you know what? I forgot a 0. Ignore that. It's going to be 100,000 times because it's 10 with 5 zeros. And so the pH 4 has 100,000 times. I'll write that better so you don't confuse. 100,000 times more hydrogen concentration than pH 9 solution. Okay, so you can see that the scale is logarithmic. It's not just 5 times more, it's 100,000 times more. Okay, because it's a logarithmic scale. Right? So with that in mind, we do have solutions out there that are considered buffers. So a buffer is basically where we have substances that minimize the change in concentrations of the hydrogen ions and the hydroxyl ions in solution. And that allows for us to survive some of these, slight changes in the environment a little bit easier. So most living cells, we like to be around a pH 7. But, we're constantly inundated with different ions and things like that. That's going to change the pH. So we need to have buffers that help stabilize or minimize those changes. So most buffer solutions contain a weak acid and its corresponding base. So there's going to be some hydrogen ions, for example, in there, and some hydroxyl. So here's an example. We have H2CO3. So H2CO3, it's going to be able to get rid of hydrogen pretty easily. So in response to a drop in the pH where we have a lot of hydroxyl ions or negative ions in there, it's going to want to, it can get rid of and donate hydrogen ions to the solution to bring up that pH. When the pH is too high, it has the ability to accept hydrogen ions in the solution. Okay, so this is going to allow it to survive changes, slight changes in the pH by either accepting the hydrogen or getting rid of the hydrogen. So this helps us explain why oceans are very, very important aquatic ecosystems, because the seawater has a natural buffer to it. So it can sustain slight changes in pH, but it can only do that to a certain point. So it can only, maintain the pH for so long. So what does that have to do with global warming? So the ocean has actually become more acidic because of global warming or global climate change. And that's because global climate change is due to the fact that we're pumping too much carbon dioxide into the atmosphere. So carbon dioxide ends up being absorbed by the ocean, because the ocean is this huge buffer, and it's going to absorb that carbon dioxide and react with the water in the ocean. So when we have carbon dioxide and water reacting, we form something called carbonic acid. So carbonic acid, if we remember, is, it can be kind of a buffer, right? So if the pH gets a little too high, it can absorb hydrogen ions, and if the pH gets a little too low, it can release them. But if there's too much carbon dioxide reacting with the water, the pH is going to go up to the point where it can't really buffer anymore. And the problem is, if we end up having too much hydrogen ions in the water, it can add up and change the structure and affect basically the formation of carbonate ions. So carbonate ions, they form something with calcium to form a calcium carbonate, which is important for the development of shells in our sea creatures, along with the formation of coral reefs and their skeletons. And so as the ocean becomes more acidic, we're making it less available to build our shells through the lack of basically calcium carbonate. And so this is going to affect how our aquatic ecosystems are forming if the water becomes too acidic. So carbonate ion concentrations actually have declined for the past 40 by a lot, by 40% by we think by 2100. And so we think as that calcium carbonate declines, it's going to basically cause this domino effect with our aquatic ecosystems. And it all has to do with the amount of carbon dioxide that's in the air. If there's too much, it changes the chemistry of the ocean. All right, so let's do a couple of checkpoint questions and then we're done. So water has special properties, including high cohesion, high surface tension, and the ability to absorb large amounts of heat per unit of mass. So what kind of bonds between water molecules give water these special properties? So we're talking about, remember, bonds between water molecules. So what are those bonds called? Hydrogen bonds, right? All right, so you should have the course objectives completely filled out now, and then you can use that to prepare for your exams and your quizzes. All right, so we are done with chapter 2. We're done with our lecture for the week. And so I'll see you in our Zoom meetings. Take care, everyone.